Hello everyone and welcome back to Minic Analytics. I'm very pleased to have you back once again. In this video, we're going to be discussing yet another supervised learning machine learning algorithm, and that will be the decision trees. We're going to be applying the decision trees in customer churn classification. Before we get started, please consider subscribing to our YouTube channel. We are welcoming you to our wonderful community. You can also hit that notification bell, like, comment, and share. And feel free to leave any questions and comments behind because we love hearing from you. Once again, thank you for joining me and let's get started. For this analysis, we will start by importing the Python libraries. So for this case, I will be using the pandas, numpy, as well as the matplotlib library, just in case we have some something that that will need visualization. So when I run this cell or I execute this cell, I will have imported the Python libraries. Okay, so the next thing will be loading our file onto the Jupyter notebook. When loading this file, I will be using the read CSV function from pandas, and as you can see inside the brackets, so this is just the file path as well as the file name, and I will be using the head method. So by the head method, I'll just be printing or displaying the first 5 rows of the data frame. The next step will be inspecting the shape of the data frame. So when inspecting the shape of the data frame, I'm going to use the info method. When I execute this using the info method, you can see that we are getting an output, and this output is just a summary representation of our data frame. From the output, you can see that the range index says that we have 7,043 entries. So in other terms, you can say that our data frame contains 7,043 rows. Also, we are getting the null count. So when we compare the null count and the range index, we are seeing a similar value. So in other terms, you can say that we don't have missing values in our data frame. And the D type, this is just the data type of the values in those columns. Under data cleaning, let's first begin by checking for duplicates. So when checking for duplicates, I'm going to be using the duplicated method. When I run this cell, you can see that from this code, we are getting an output of 0. We can see that we don't have duplicates in our data frame. Also, another thing that I said about data cleaning was checking for, if you don't want to use the info method, you can just use the isNull method. Okay, so from the output of using this line of code. Also, under data cleaning, you can see that under the column total charges, you can see it's being represented as objects. But when we look at that column, we can see that total charges, we expect that the values, or it needs to be indicated as floats. But from here, you can see it's being the values under the columns are being represented as objects. So to tackle that problem, the only thing that we can do is perform some mathematical calculations. So we have the column tenure and we have the column monthly charges. Tenure can represent the time that company has been having that client, and monthly charges can represent the monthly charges that that client has been paying for the internet service. So what we are going to be doing is that we are going to be multiplying the values tenure. We are going to be multiplying with the values in the monthly charges column for each customer, and after we are going to be storing our values under the total charges column. So the total charges will represent the sum of the charges that the customer has been paying to the company. So we'll be calculating the total charges for each customer. From our function, we are going to return a product of tenure and monthly charges, and I will use the lambda function. When I run this function, you can see that column total charges will now be the product of tenure and the monthly charges, and to see if you have transformed the data type of the values under the total charges column. So I will just use the info, and from the results, you can see that in the total charges column, we have now changed that to float. Okay, so that's how you can correct that. You can see it's printing out the columns in the data frame, and from the numeric value, we are seeing we are getting zeros. So by this, you can see that none of our columns are having missing values. Because this is a binary classification example, so in the column churn, this will be our target variable, or in other words, this will be our independent variable. Before we jump right into building our model, I'm going to check for class imbalance in this data frame. So class imbalance is a situation that occurs when one or more classes in the target variable have significantly fewer instances than the other classes. In other words, one class is underrepresented while another class or classes are overrepresented in the dataset. The major impact of these class imbalances is that it can lead to biased model performance, and in most machine learning algorithms, the model tends to favor the majority of the classes. If you have one class that is overrepresented, the model will favor that class because it has more examples to learn from. As a result, the model may perform poorly in predicting the minority classes. The first thing that under class imbalance, I'm trying to find the unique values under the churn column. When I execute, you can see we are getting our output is an array showing the unique values in the column churn. So as you can see, we have no and yes. For this case, in this analysis, no will represent that the customer is still using the service, while yes will be indicating that we lost the customer. So while checking for class imbalance, I'll just perform a value count for instances of no and also for instances of yes, and plot a pie chart to represent this information. From the output, you can see that we have 5,174 instances of no and 1,869 instances of yes. So let me plot a pie chart to represent this information, then I can then explain further. This is our pie chart, and this pie chart shows the class distribution. For instances of no, in terms of distribution, we at 73.5%, and instances of yes is at 26.5%. So 73 and 26, you can see that we, in some way, we can say that we have a class imbalance. So in one way or another, the class imbalance will affect the accuracy of our model. There are various ways you can deal with class imbalance, but that falls beyond the scope of this analysis. With feature selection, we are trying to select the features that we will be using in our analysis. We have a total of 21 columns, and I won't be using each and every of these columns. I'll be dropping some of these columns, but before we drop those columns, or before we decide which column are we going to drop, I'm going to perform a correlation test, and because most of our values are categorical values, I'll be employing the chi-square test to compare these categorical columns with the target variable, which is the churn. So for our hypothesis, we have the null hypothesis as well as the alternative hypothesis. Our null hypothesis states that there is no significant effect or difference or relationship between columns and the target variable in the data. So our null hypothesis is that there is no significant effect, difference, or relationship between columns and target variables in the data. And by this, it will be representing absence of any effect between the columns that we will select and our target variable churn. And for the alternative hypothesis is that there is a significant effect or a difference or a relationship between the columns that we will select, as well as the target variable in the data. So we'll do, by performing our chi-square test, we will get the p-value, and the p-value is the one that we will be using to test for significance. So I will select a p-value at 95% confidence level, so that will be 0.05. That will be our p-value. The first thing will be creating a list, and this list will contain all the columns that we are going to be comparing with our target variable. So, and I forgot we need first to import the chi-square modules. SciPy stats, import the chi2 contingency. Then we create the columns. So these are the columns that we are going to be comparing against our target variable to check if there is a significant difference. So then I'm going to initialize an empty list, or I'm going to create an empty list that will be storing our results. So we'll label it as chi-square results. So then I'm going to define the significance level, and I'm going to set the significant level at 95%, so or 0.05. We are now going to perform a chi-square test for each categorical column. I'm going to use a for loop that will be iterating over the pre-selected columns. So for columns in categorical columns, so it will be iterating over the different columns in the categorical columns list that we created earlier. And then we create a contingency table. We'll be using the crosstab class. So it will be comparing the individual columns and comparing with the target variable to determine if there is a significant difference. And since we are dealing with different columns, we will append our results to a list. Once we have appended our results, we create a new data frame from the results list, and then we display our output. As you can see, from the different columns, we are getting different chi-square value as well as the p-value, and a test if it is significant or not. True indicates that there is a significant difference, while false represents that there is no significant difference. So when we are going to be selecting the features, I will include all these features except for the phone service. I will start by importing the modules that we are going to be using for this analysis. So those include the decision tree classifier. We are dealing with classification, so I'm importing the decision tree classifier. In our analysis, we will be splitting our data into training set and testing set. So we'll be using the train test split. We'll also be evaluating our model. So we'll be using the classification report and also the accuracy score. Most of the features that we're going to be using are having categorical values. We need to change those categorical values and assign those values to numeric values. So we'll be using the label encoder, and this will assign distinct numeric values to the categorical values. Also, the confusion matrix and the F1 score, this will be used when evaluating the efficiency of our model. Now, I'm going to select the final features that are going to be used in the model. So I'm going to do a feature selection. So the final features that we will be using in this analysis, those features include gender, senior citizen, partner, dependents, tenure, multiple lines, internet service, online security, online backup, device protection, tech support, streaming TV, streaming movies, contract, monthly charges, as well as total charges. So those are the final features that I'm going to be using in our model. I need now to use the label encoder to assign numeric values to the categorical values. The first thing that I'm going to do under label encoding is that I'm going to specify the columns to encode. So the next step will be creating a copy of the data frame with the selected columns, so that when I start encoding, I won't be affecting the columns that already are in numeric form. The encoded columns, so features.copy. So I'm creating a copy of the features data frame, and once I'm done with that, I'll be saving in a new variable, which will also be our new data frame that will contain the columns that I'm going to encode. So once we have created a copy, I'm going to start the label encoding process. So with this line of code, I'll be encoding the columns with containing categorical values, and then I print the output. So when I run this, you can see that I have encoded, I've assigned numeric values to the different categorical values in the selected columns. So earlier on, as I said, since we created a copy, we did not interfere with the numeric columns in the columns that we left out, such as the monthly charges, total charges. So we did not assign new numeric columns to those values. As I had said, step number 3 will be defining the independent as well as the dependent features. So for the X, which represents our independent features, so those are all other columns except churn. And churn, since it is our target variable, so it is the dependent variable. So the X's, these are the predictors, or in other words, we say these are the independent features or variables. Then our Y will be the target variable, which is the dependent feature, and it contains the classes that we are going to be predicting. And for data splitting, we are going to split the data set into the training and the testing sets. And for this case, 80% of the data will be used for training and 20% will be used for testing. So X10, X train will be the variable that is going to store our data that will be used for training. Xtest will store the data that will be used for testing. Ytrain will be used to store the target variables for training, and the Ytest will store the target variables for testing. Okay, and if you want to determine the dimension of the 4 different data sets, so that's the Xtrain, Xtest, Ytrain, and Ytest, you can use these lines of code. By this, by printing the shape, we are going to be displaying the dimension, the dimensions of each variable. So when I run this, for example, for the Xtrain, Xtrain typically represents the training data of the machine learning model. So okay, and when we see a figure 55634,16, it means that there are 5,634 data points and 10 features in the training data. When building this decision tree model, we start by creating the decision tree classifier. So the decision tree classifier, then we are using the random state of 42. So these are just some of the hyperparameters that we will be using. So you can get all the hyperparameters and their values by using this line of code. So by using this, it will be printing out all the hyperparameters in the decision tree classifier model that you are building. So when I execute this, you can see that we are getting different types of hyperparameters. Okay, so for the CCC alpha, you can see 0.0, class weight, none, criterion, entropy. So we specify that we are going to be using entropy. So as you can see, we have now fitted the model to the training data. Okay, so the Xtrain and the Ytrain. So we are going to make predictions on the testing set data. So you can see we are getting an output of zeros and ones. So zeros and ones, these are the classification. I'll use the classification report as well as the accuracy score, and I will also use the confusion matrix. The first one will be the classification report. From the classification report, we are getting the metrics such as precision, recall, and F1 score. So when we are talking about precision, this is the measure of how many predicted positive instances are correctly predicted by our model. In this case, class 0, we are getting a value of 0.83, which means that 83% of the instances predicted as class 0 were indeed class 0. For class 1, it's 0.43, indicating that 43% of the instances predicted as class 1 were correctly classified or were of class 1. When we look at the accuracy of our model, accuracy often reflects the overall rate of correct predictions. The accuracy score is approximately 71.2%, which means that our model is correctly predicting about 71.2% of the instances. The confusion matrix will provide a detailed breakdown of the number of correct and incorrect predictions. There are 170 instances where the model correctly predicted the positive class. So that is the class number 1. And for the true negatives, there are 842 instances where the model correctly predicted the negative class. And for the false positive, we have 288 instances where the model incorrectly predicted the positive class. So it predicted 1, but the actual class was supposed to be 0. And for the false negative, there are 169 instances where the model incorrectly predicted the negative class. So in this case, it predicted 0, but the actual class was 1. But for this analysis, there's one thing that I will be adding. That will be the grid search for hyperparameter tuning. So a grid search is often used for hyperparameter tuning. This is a technique that is used to find the best combination of hyperparameters for a given model. Hyperparameters, these are settings or different types of configurations that are set prior to training our model. So by default, these models come with already set hyperparameters. Finding the right value of hyperparameters is very crucial for achieving the best result of our model. So the steps that I'm going to be using under the grid search is, number 1 will be hyperparameter set selection. So I will specify the set parameters and the range of the values or options for each hyperparameter that I'm going to select. Then number 2, I'm going to create a parameter grid. I'm going to use a grid search algorithm which creates a grid of all possible combination of the specified hyperparameter values. Then after that, step number 3 will be model training and evaluation. Then step number 4 will be selecting the best combination. After evaluating all the combination, the grid search algorithm will identify the combination of hyperparameters that results in the best performance. Then you can then use the model with the best hyperparameter setting to make predictions on new unseen data. I will start by importing the relevant modules. I'll start by defining the hyperparameter grid. You can also classify this hyperparameter grid as the parameters that we are going to be selecting. So for this grid search, I've selected a few of the hyperparameters. The first one is the CCP alpha. I've selected 2 values to consider. So that is 0.0 and 0.1. The next one is the criterion. I've selected Gini as well as entropy. So those are my 2 options. For max depth, my options are 1 and 5, while for max leaf nodes, my options are 2 and 5. So if you have other parameters, you can just be adding below here. We're going to create a decision tree classifier model. So this is the decision tree classifier model, just as we did earlier. And in this, I've specified the random set as 101. So by creating this decision tree classifier model, it will serve as the base model for which we want to find the best hyperparameters. Then after this, we are going to initialize the grid search. By using the grid search cross-validation, it's going to perform a search over the specified hyperparameters values, and it will take the base model that we have already selected, the parameter grid, and the number of cross-validation faults it's going to be doing. So then after this, I'm going to fit the grid search to my data. This will train and evaluate the model with different hyperparameter combinations for each fold of cross-validation. After this, we can then print the best score of, and the best parameters. After the grid search is complete, as you can see, we are going to print the best score and the best parameters found by the grid search. The best score will represent the highest score validated performance metric. Oftenly, it is usually accuracy or another scoring metric that can be used, while the best parameters shows the set of hyperparameters that resulted in the best score. So when I run that, you can see that the best score is showing at 0.775, which is a little bit higher than what we got earlier, 0.71. And it's showing us the best parameters. So we are going to use these parameters in the new model that we will be creating. So the random state was 101. Criterion, we are going to use Gini. Max depth 5, max leaf nodes 5. Then we are going to fit that to our X-train data and our Y-train. Then make predictions. After making predictions, we are just going to go directly to our model evaluation. For our new model using the new hyperparameters, so from the precision score, we can see we are having significant changes. We have improved in terms of the accuracy, so from 71% to 79%. Also in terms of precision, from 71% to 79%. And we can also see some change in terms of our confusion matrix. So when we look at the confusion matrix, the first table is the initial model, while after grid search, this is the output. So the confusion matrix after grid search shows different values of true negative, false positive, false negative, and true positive compared to the initial confusion matrix. In particular, there are more true negative and fewer false positive after grid search, indicating a better balance between correct predictions for both our classes. So in summary, we can conclude and say that the grid search for hyperparameter tuning has led to an improved model with better overall accuracy, indicating a more reliable classification performance. That's all for today. We have now reached the end of the analysis. Once again, thank you for joining me today. And before we sign off, please consider subscribing, hit that notification bell, like, comment, and share. And until next time, see you.